Hi, everyone. Welcome to the UFS webinar. We'll probably give people about 1 more minute to show up, and then we'll get started. Okay, it is just after 3 o'clock, so we can go ahead and get started. So welcome everyone to the UFS webinar. My name is Karen Keith. I am filling in for Bhavana this week, and I'm in the NWPS STI modeling division. And just some housekeeping information, the UFS portal can be found at ufscommunity.org. And if you want more information about these webinars, on the very bottom of the page, you can subscribe to the webinars, also look at past webinars on YouTube, and then see what the upcoming webinars are going to be. For today's presentation, it'll be 45 minutes long, and then there's 15 minutes at the end for questions and answers. Please put any questions into the question box on the right-hand side in your GoToWebinar control panel, and I will read them out after the presentation is done, so you can type them in anytime during the presentation. Okay, I will pass it over to Avishal for the introduction.
Thanks, Karen. Good afternoon, everybody. This is Avishal Mehra from EMC, and today it's a pleasure to introduce one of my colleagues and friends, Dr. Vladimir Krasnopolsky. Vladimir received his master's in theoretical and computational physics and his PhD in theoretical nuclear physics from Moscow State University. He worked in the field of theoretical nuclear physics at the Institute of Nuclear Physics in Moscow before coming to US in 1989. Since 1990, he has worked in the field of numerical weather and climate modeling and AI applications. He developed multiple neural network applications in numerical weather and climate modeling and continues to do so. Vladimir has published 2 books, 2 book chapters, over 70 papers in refereed scientific journals, and more than 100 technical and conference papers. He is a member, formerly chair, of the Committee on Computational and Artificial Intelligence Applications in Environmental Science of AMS. He remains a member of the IEEE Computational Intelligence Society Task Force and is also a member of the International Neural Network Society Working Group. He's also a member of the NOAA AI Executive Committee. In 2018, in recognition of his work, Vladimir was awarded by AMS a Distinguished Scientific Committee Award for his contributions to advancing the application of artificial neural networks to Earth science problems, and in particular, emulations of complex multidimensional mappings. So I would like now to hand it over to Vladimir so that he can today talk to us about hybridization of physics-based modeling with machine learning in numerical weather climate modeling systems. Vladimir?
Thank you, Avishal, and good afternoon. So in my presentation, I would like to make several points, and here you can see these points. First is that NOAA scientists have been developing machine learning applications for numerical weather and climate modeling systems and related fields for about 25 years. It's not machine learning, it's not something very new for our community. So wide spectrum of hybrid approaches, hybrid means physically based combined with machine learning, has been developed in this field. Hybrid approach is a synergistic approach. It gives you additional advance options as compared with simply physical and machine learning approach. Machine learning is a toolbox of versatile nonlinear statistical tools, and it can solve or alleviate many problems, but not any problem. And machine learning has a very broad but limited domain of application. So, okay. I will first talk about purely machine learning approach based on data only. Then I will talk a little bit about physically based modeling, which is based purely on physical first principles. Then I will introduce different hybrid approaches and show several examples of hybrid approaches of different types of hybridization in the model. The spectrum of hybrid approaches is very broad. I put here on the several spectral lines and many more. But first, I will talk about Paul's limits of this spectrum. A machine learning forecast model which are based only on learning from observations, and forecast models which are based purely on physics first principles. Let's start with machine learning. What is machine learning? Machine learning is a subset of artificial intelligence. Simply speaking, artificial intelligence is machine learning plus hardware. Machine learning provides software, and plus hardware, it will be artificial intelligence, like in robotics, in driverless cars, self-driving cars. So machine learning algorithms build mathematical statistical models based on training data. Machine learning is learning from data approach. No data, no machine learning. So machine learning toolbox includes great variety of tools. Several of them are shown here, such as support vector machines, decision trees, artificial neural networks, Bayesian neural networks, genetic algorithms, and practically every couple of months, new advanced machine learning tools emerge. I will focus on artificial neural networks, or simply neural networks, because in the field of numerical weather climate modeling, the majority of applications have been developed and are being developed using neural nets. But there are a lot of different types of neural nets: shallow neural nets, deep neural nets, convolutional neural nets, recursive neural nets, and so on and so on. I will introduce here, before talking about machine learning tools about neural networks, a mathematical notion which is called mapping. It's important notion when you are talking about machine learning in numerical weather modeling. Practically all applications, all part of this system, weather climate modeling system, are mapping. Mapping is a relationship between two vectors or between two sets of parameters. And as I said, majority of components of numerical weather and climate prediction models are mapping. On the other hand, machine learning tools such as neural network, support vector machines, decision trees are generic tools to approximate complex nonlinear multidimensional mapping. So there is a match between machine learning tools and applications in numerical weather and climate modeling. Both are mappings. So now let me introduce the simplest machine learning tool. It's a multi-layer perceptron, and simplest multi-layer perceptron is shallow neural net. Neural net is a network of similar or identical elements. In multi-layer perceptron, neurons are situated in two layers. There is always one input layer, one output layer, and one or several hidden layers. If we have only one hidden layer, this neural network is called shallow neural net. If we have several hidden layers, it's deep neural net. We will consider shallow neural network. You will see it's very powerful tool. Let's look inside the neuron. Neurons have multiple inputs and single output. And generic neuron consists of two parts: linear part, which calculates linear combination of inputs, and then this linear combination goes into nonlinear part as an argument for activation function phi. This activation function is essentially a nonlinear function. This is why the output of neuron is nonlinear function of input. It can be symbolically written in this way. If we assume that activation function is hyperbolic tangent, then it will be explicit equation for the neuron. It's simple enough. Now let's make additional assumption that in output layer our neurons are linear. They don't have this nonlinear part. Then we can write down outputs wise as simply linear combination of outputs of hidden neurons T. And substituting T, we will see that shallow neural net is very simple, actually, combination of several hyperbolic tangents. So it's simple. If you calculate it, it calculates very fast. And as I said, it's mapping actually, because it's mapping between input vector and output vector. And this tool is extremely powerful, mathematically proven that this simple neural net, shallow neural net, can approximate or model any, I stress, any continuous or almost continuous mapping, complex, nonlinear mappings, continuous, almost continuous. Almost continuous means that this mapping has discontinuity, finite discontinuity, something like step function. So now let's summarize what we learned about machine learning models, machine learning tools. Approach is simple. First, we train machine learning model, for example, shallow neural net or deep neural net, using training set. Then we validate this model using independent validation set, and then neural network is ready for use. Then you can use it. Advantages of this approach. Approach is backed by math, and as I told you, math has proven that shallow neural network approximate any complex nonlinear multidimensional mappings. A relatively simple approach and model. You could see previous slide, it's a combination of hyperbolic tangent. Requires only data for development. And fast. Again, simple combination of hyperbolic tangent. Limitations. Limitations are reverse sides in some sense of advantages. It may be too simple to model complex multi-scale system. For example, I think currently we don't have machine learning tool which can emulate entire numerical weather and climate modeling system. It's too complex for machine learning. However, some components that I will show you can be emulated. So it's completely dependent on data. If your data is not good enough, and observations are usually sparse in space, time, and scales, then you cannot train good machine learning tool because you will not get good generalization. Generalization means extrapolation as well as interpolation. And this generalization may be unstable if your data set is not sufficient, if it's not represented. So now let's look at the opposite side of the spectrum, on the model which is based only on physics, on physical first principles. I will talk about it very quickly because you are all very well familiar with general circulation models like our GFS, CFS. So it's based on a set of conservation law and on 3D partial differential equations, system of 3D partial differential equations of the sphere. And symbolically it can be written in this way, and B is model dynamics or result physics, and P is model physics, which effectively parameterize subgrid processes. And it's time-consuming component, very time-consuming component. For computational reasons, model physics is 1D, it's columnar. But it's still, even after this drastic approximation, it's still time-consuming. What kind of limitations has this approach, physically based approach? The left figure, I think you maybe saw this figure many times, but let's again look at it. Horizontal axis shows model resolution. It increases from the left to the right. It becomes finer and finer. Left vertical axis shows number of computer cores which we need to resolve to calculate such resolution, to calculate a model with such resolution. And doubling of resolution requires 8 times more processors. It's nonlinear dependence. So, and right vertical axis shows power consumption. And red line, horizontal red line shows affordable power limit. And you see that our ensemble systems have already hit this ceiling, this affordable power limit. It means that if you want to increase a number of ensemble members, you need to reduce resolution or vice versa. Single member systems will hit this limit very soon. Also, processors become faster. During the last several years, we observe some saturation in processor speed. So machine learning can alleviate this problem through speeding up model calculations, and I will show you examples. Another challenge, model physics. With increased resolution, scales of subgrid processes become smaller and smaller, and subgrid processes still need to be parameterized, and small-scale physical processes are often more complex than large scales. The physics is more complex. It means that parameterizations are more complex and more time-consuming. Or in some cases, we don't understand completely the physics of this small-scale process. In this case, we cannot build physically based parameterization. And here, machine learning can respond to this challenge in 2 ways. First of all, it can speed up calculations of existing parameterization, developing fast machine learning accumulation of this parameterization. And if we have data, we can develop fast new machine learning parameterizations based on the data. Okay, so let's again talk about this pattern of hybridization. As I said, we consider two poles, two limits. And this is why idea of hybridization emerged, because both of these purely machine learning and purely physically based approaches face some problems. And our hybridization of this approach, combination these components, physically based and machine learning components, the model, provide hybrid approach, which is synergetic, as I will show you. It gives new opportunity, advanced features, which both of these approaches by themselves don't provide. So I will show application of machine learning in data assimilation system and model physics, parameterizations and model physics, and in post-processing. You cannot touch, for example, general circulation model, UFS, for example, and leave it as it is, physically based, but then you use machine learning tools in post-processing to improve model output. So I will show you examples. Here, I show different kind of hybridizations, which is used to improve numerical weather climate modeling systems. This system consists of three major components: initialization component, data assimilation, model itself, and post-processing. And in all these components, we can hybridize, provide for all of them hybridization approach. For example, for initialization, we can develop better machine learning retrieval algorithms to improve and combine them with physically based, statistically based data assimilation system. We can develop fast forward models to improve direct assimilation, to speed up direct assimilation of satellite measurements. We can develop machine learning observation operators, which allow you to propagate instantaneously surface signals vertically. For the model itself, all these applications have been already developed. For model physics itself, fast model machine learning radiation has been developed. New machine learning parameterization. There are a lot of works now which are devoted to develop new moisture parameterization for machine learning moisture parameterizations. Fast machine learning physics, complete physics can be emulated with machine learning. I will show you this example. For post-processing, bias correction, nonlinear machine learning, ensemble averaging. I will show you this example. Nonlinear MOS is possible. Now let's switch to examples. First examples is hybridization in DAS, ingesting satellite data. To ingest satellite data in data assimilation, two mappings are used. Retrieval algorithm and forward model. They both are mappings between two vectors, vectors of satellite measurements and geophysical parameters, vector of geophysical parameters. And a machine learning or neural network can provide fast, accurate retrieval algorithms and fast forward models for direct assimilation. Let me show you a retrieval algorithm, example of retrieval algorithms. These two figures show mid-latitude winter storm as it was retrieved by SSMI wind speed satellite retrieval algorithms. It's wind speed, and this color table shows wind speed and nodes. Left panel shows this wind speed field retrieved by regression algorithm, and you can see a lot of white caps. why they appear here. Regression algorithm cannot resolve very nonlinear complex situation in the center of the storm. There is high level of water vapor, high level of liquid water, high wind speeds, and regression algorithm cannot resolve these signals. It's too nonlinear for regression. Neural network can successfully resolve these signals and provide retrieval in the center of the storm. So, significantly improve retrievals because this area in the center of the storm, high wind speeds, they provide the major impact in data assimilation system. Second example is hybridization in UFS, an emulation for parameterizations. Here, original long wave radiation parameterization based on radiation the radiative transfer is shown, and neural network emulation of this parameterization. And why neural network emulation is provide big speed up, which I will show on the next slide. You can see here original physically based parameterization. At each time step in each grid point evaluates two integral equations, and coefficients of these integral equations has to be derived from solution of integral differential to the integral differential equations. And at each time step, in each grid point, all this number crunching is performed. This is why radiation parameterizations are computational bottleneck in model physics. With neural net, you need to estimate, as I showed you before, simple sum of hyperbolic tangent. But of course, to find coefficients of this neural net, you need to run original model with physically based radiation sufficiently long to generate a representative data set to save inputs and outputs of original parameterization physically based, which constitute a training set for neural net. And then train neural net. Training is time-consuming project process also, but you need to do it once. After you train neural network, you for a long time can use this fast neural network emulation. And here in this table, you can see what kind of speed up provide this approach. It's physically based parameterizations are RTMG, long wave and short wave radiation parameterization, which I used in UFS, and majority of major layer and weather prediction use these radiative parameterizations. So it's 1 or 2 orders of magnitude speed up. And for cloudy counts, speed up is higher. Why? Because for original radiative transfer parameterization, the heavier is cloudiness, the slower is calculations. For neural net, it's the same sum of hyperbolic tangent. It allows you, in addition to speed up, balance better performance in multi-processors regime. Otherwise, with physically based parameterization, processors with cloud sky works longer, and processors with clear sky wait for cloudy sky processors to complete their calculations. There are a lot of idle times. Using a neural network, they remove this idle time and balance computational performance. Also, neural network emulations are unbiased, which is very important because systematic errors are major errors which accumulate in the model. So neural network is fast, but is it accurate enough? Here you can see individual heating rates profile for long wave radiation. And complexity of profiles increases from the right to the left. It means that cloudiness situation becomes more complex from the right to the left. And black line shows profiles from original radiative transfer RTMG parameterization. And you probably cannot see this black line only in several places, because actually neural network approximation is very good. A red curve shows neural network, shallow neural network with 100 neurons in hidden layer, and blue with 150 hidden layers. And you can see that when, for example, here, when red is not perfect, blue corrects this approximation for this spike. So, but the major test for these machine learning components like neural network parameterizations are in parallel runs when you couple it into the model instead of original parameterization and perform parallel run, control run, which is shown on the upper left with RRTMG, long wave and short wave radiation, and run of hybrid model where we have neural network, short wave and long wave radiation. And lower right shows the difference. To convince you that the difference is very small, negligible. On the right, lower right shows the difference between two control runs with completely physically based model with physically based parameterizations, but with different versions of compiler. The difference between two runs are different versions of Fortran compiler, because model is very nonlinear, and precipitation rate, which is shown here, it's a very nonlinear parameter. Of course, even round of errors. The difference between these two runs are round of errors. Even round of errors cause some difference between runs, but nobody can argue that these differences are negligible. And you can see that differences which neural network introduced are as small as differences due to round of error. Second example, which I show you, it's our very recent development. It's a proof of concept, actually. Here we emulate entire atmospheric physics suite with neural network. This suite consists of more than 10 parameterizations, and everything is emulated by one neural net. It's a big neural net with 522 inputs and 304 outputs. It has 250 hidden neurons in one hidden layer. And it's our first attempt, but even this first attempt is also already 3 times faster than physically based atmospheric suite. And it's rather accurate. For validation, we perform 24 parallel runs for 10 days forecast, uniformly distributed over an entire year. And no signs of instability were observed. The upper row shows results from a hybrid model where atmospheric physics is emulated by neural net, and lower row shows control runs. And you see that they are very similar. The difference is actually you cannot see by the difference, even for such nonlinear sensitive values as total cloudiness and cloud tendency. So Now let me show you example of several examples of application of this hybrid method of in post-processing. You know that we have ensemble systems, atmospheric model or wave model, and usually results of these ensemble members of the ensemble systems are simple arithmetic mean of ensemble members. It's called conservative ensemble, and it's a very primitive way of extracting information from ensemble members because it completely neglects nonlinear correlations between ensemble members. All ensemble members are taken with the same weight. If you have past data for this value for ensemble members, you have archive, and if you have observations, you can train neural net which has ensemble members as inputs, and nonlinear ensemble mean you can train using past observations. This approach has at least two advantages. It can pick up nonlinear correlations between ensemble members, and I will show you such example. And additional data can be introduced. Any additional data which you believe can improve your nonlinear ensemble mean can be used. There is no place in conservative ensemble to use additional data. So first example, which I show you, it's a global neural network wind wave model ensemble. We have a global wind wave model ensemble, which consists of 21 members, and upper row shows conservative ensemble, bias of conservative ensemble, arithmetic mean actually, versus altimeter data. And you can see that there are areas with very significant bias. These are two variables are shown. Left column is wind speed at 10 meters height, and right column is significant wave height. And the lower row shows neural network nonlinear ensemble. And you can see that a reduction in bias is very significant, especially in the areas where we had for conservative ensemble big biases. Second example is very interesting because it shows how may be important nonlinear correlations between ensemble members. It's a CFS ensemble which predicts 2 meter air temperature for week 3 and 4. You probably know that this window is the worst case for the model. It has lower skills in this time window. And you can see it here. Upper left shows observed anomaly in 2 meters air temperature. And lower left shows CFS ensemble, sorry. It's a regular standard ensemble with arithmetic mean. You can see that it's in antiphase where anomaly observed is negative. Here it's positive. When it's positive, here it's negative. And multiple linear regression, you can, if you have past data, you can train multiple linear regression, but it doesn't help. Also, neural network reveals correct pattern. Negative, negative, positive, positive. This entire result is due to the fact that neural network takes into account nonlinear correlation between ensemble members, which standard ensemble mean or multiple linear regression cannot take into account. It's not capable. Now let's review our hybrid approach. So approach now consists of 3 steps. First 2 steps are the same as for machine learning approach, which is purely machine learning. You train machine learning component using training set, and you test it using independent test set. But the most important third part is validation of machine learning component inside the hybrid model, running parallel runs. Advantages of this approach. Hybrid approach uses simulated or mixed data, and simulated mixed data have less noise. The level of noise is lower in simulated data especially. And they are less sparse. Simulated data, for example, they are not sparse. And you can generate very representative training set with simulated data. Second is hybrid approach speed ups model calculations. And this speed up can be used to improve the model, improve resolution, increase number of ensemble members. Then it can learn not well understood physics from data. It means that it can improve physics, provide better physics. And these 2 advantages show that this approach is synergetic. It provides you with opportunities, with options which are not in components separately. So the sum is more than arithmetic sum, and this is synergy. Limitations of this approach. Of course, accuracy of hybrid approach depends on accuracy of machine learning component. And the accuracy of machine learning component depends on the representative data set. But of course, as I said, because simulated data are used here, or mixed data, it's usually you can generate very representative data set. And machine learning component, if they are not sufficiently accurate, they can lead to instability of hybrid model. Okay, here I will skip it. Here I give you a list of developed neural network applications for model initialization, for model physics, for the numerical model itself, for post-processing with some references. And additional references are at the end of this PowerPoint presentation, which I think will be available online. Now, summary. Hybrid approach is synergetic approach that provides new advanced capability in numerical weather modeling systems. I think I showed you this. There is no free lunch, of course. Machine learning parts of hybrid approach has limitations, and I talk about these limitations. It requires data. It requires more data than linear approaches, as any nonlinear statistical approach. As any numerical models, machine learning applications should be periodically updated. However, machine learning can be updated online. I didn't have time to talk about it. Interpretation of machine learning models as nonlinear statistical models, it's the same, is not obvious. And there are a lot of works that have been done recently to provide some tools to interpret these black boxes, to make them gray, not black but gray, halfly transparent, or partly transparent. And I don't know how many shades of gray, 50 shades of gray, or more can be developed, but I'm sure that it will still be gray boxes. You cannot do, in my opinion, machine learning boxes completely transparent. More things to consider. Shallow neural networks is a mathematical solution for machine learning problem. Vladimir, who is founding father of machine learning, showed it in his recent work. In the same work, he state that from theoretical point of view, deep neural nets cannot guarantee solution of machine learning problem. It should be considered as heuristic approach. And deep neural networks are very popular now, very fashionable tool, new tool. Does it mean that we shouldn't use deep neural network? Not of course, but we should be very accurate when we use deep neural network. First of all, deep neural network require significantly more data for training. Why? Because when you add additional hidden layers, the number of weights of this neural net, deep neural net, and these weights should be trained, the number of weights increase dramatically. And you need more and more data to train this neural net, and not always you have more data. Deep neural networks may become excessively nonlinear, again with adding new and new hidden layers. Deep neural network model becomes more and more nonlinear, which may lead to unstable extrapolation and even interpolation, or in other words, instability when integrating inside hybrid model. And there are a lot of works we recently published which report such kind of instability with deep neural net. So again, it doesn't mean that it shouldn't be used, but you need to remember that parsimony principle is still valid, and complexity and non-linearity of your model, machine learning model, shouldn't exceed complexity and non-linearity of the system which you model. And finally, my last slide, it shows that NOAA is a leader in this field and application of machine learning for numerical weather and climate model systems. The medium timeline shows development which was performed in NOAA during the last 25 years. And for comparison, there are two timelines which show ECMWF and UKMO. In UCMWF, in the beginning of 21 machine learning applications has been developed, neural network long hybridization from data assimilation. But then they stopped working in this area. Only a couple of years ago, they started again working in this area. In UKMO, nothing was done in this area before 2018, and only then they started working in this area. But they have now big groups of very highly qualified people with good funding who are working in these areas. And now they repeat what we did 10, 15 years ago. But very soon, if we don't invest in this area, we may lose in several years our leadership. Questions?
If anyone has any questions, please type them in the question box in the GoToWebinar control panel.
Okay, while people are thinking about questions, let me say several words why I choose such topic for presentation.
Oh, sorry, there's one question, Vladimir.
Okay.
Someone asked if you can show the slide on NN for DAS again.
Yes. This one?
The summary slide.
Yes. I didn't say that this algorithm has been developed almost 25 years ago and was introduced in our operational data assimilation system in 1998, and it served well in this data assimilation system for almost 20 years till they started to assimilate directly SSMR brightness temperature. Then it was not needed anymore.
Okay, there's another question. It says, for the GFS V16 with ML, how did the usual forecast verification statistics results compare against the regular GFS V16?
Okay. If you mean this slide, so it shows comparison between hybrid run with NN physics with control run with regular physics package. And here is a bias, and you can see that the bias is very small and figures is very similar. It's actually its first results, it's proof of concept. We will work on these projects more, of course. And I think now we have only 3 times speed up, 3 times faster than original physical package. I think we can reach more significant speed up.
Okay, last call for any more questions. Oh, sorry, one more. Would you mind explaining more about what is meant by the second bullet point on the more to consider slide number 31? Why is DNN a heuristic approach?
Oh, you know, I can give, if you give me your email, I can give you reference to this work, Wapnick's work, recent last year it was published. And what he showed that generic mathematical solution for machine learning problem is shallow neural network. And deep neural network, from mathematical point of view, cannot guarantee solution of machine learning problem, or at least optimal solution. This is why he says that it should be considered a heuristic approach. It doesn't mean that probably in the future somebody proves that it's a deep neural network is also provides also mathematical solution for machine learning problem. But at least now, what was proven that a mathematical solution is shallow neural network. However, even without this work, as I said, a lot of papers report instability when using deep neural nets. And it means that actually it could be well understood the source of this instability. As I explained, the more the more hidden layers you have, the more data you need. And sometimes people don't have so much data as they need, and they train deep neural net on insufficiently representative training set, and then they get instability. Or their deep neural network is exceedingly nonlinear. The system is not such, doesn't have such high nonlinearity as the deep neural network have. And again, it leads to instability. I simply try to say that you need to be very accurate when you work with deep neural network. It's a very good tool, but it requires even more accuracy. Of course, you need to be accurate with any machine learning tools because they are nonlinear, and nonlinear tools are very tricky sometimes, and they require great accuracy. but deep neural networks require more accuracy in working with them than, for example, shallow neural nets. I don't know if I answered your question.
There's one more question.
Yes.
Oh, and the last person did say thanks to that, so I think we're good. Last question. For the full suite physics NN, does NN emulate each component of the physics suite, or it only emulates the whole suite?
No, it doesn't emulate each component. It's exactly the point that one neural net emulates the whole suite, and it has the same inputs as the whole suite of model physics and the same outputs. So it's like, you remove one chip and put another chip with the same inputs and outputs. So, and this chip, new chip, is 3 times faster and gives you the same, almost the same accuracy that you could see. But again, I emphasize that it's pilot studies, proof of concept. First results, they are very good, but we need to work more on these results.
Okay, and that's all the questions we had, and we're just about out of time. So thank you very much, Vladimir.
And thank you, and thank listeners for listening.
Yes, thanks everyone for joining today.